In this podcast episode, Dr. David Sinclair shares groundbreaking insights into the frontier of aging research and human longevity, emphasizing the profound impact artificial intelligence, AI, has had on accelerating discovery and drug development. The conversation covers the biological mechanisms behind aging, innovative approaches to reversing age-related decline, the cultivation of human brain organoids in the lab for Alzheimer's research, and emerging therapies that hold promise for neurodegenerative diseases, blindness, and fertility. The discussion also touches on practical health protocols, the role of lifestyle factors, and ethical considerations related to growing human tissues. Dr. Sinclair highlights AI's transformative role in speeding up drug discovery and aging research. Traditionally, screening billions of chemical compounds for age-reversing potential would take centuries and billions of dollars. AI enables virtual docking of vast chemical libraries against detailed protein structures elucidated recently by breakthroughs like those from Demis Hassabis's team at DeepMind. This approach replaces costly gene therapy techniques with oral or topical drugs, democratizing access to therapies that can reverse aging markers in cells. AI combines brute force computational power with advanced pattern recognition to extrapolate molecular interactions across atoms, proteins, and biological systems. Importantly, Sinclair's lab has built its own AI models tailored to classify young and old human cells based on complex visual patterns, achieving an ability to detect subtle aging signatures without direct instruction. This level of AI-enabled pattern recognition is instrumental in screening and prioritizing candidate molecules before moving to costly lab validation. Central to Sinclair's research is the notion that aging is fundamentally an information degradation problem at the cellular level. Cells lose the ability to correctly read their genetic and epigenetic information over time, akin to errors accumulating on a scratched CD. This degradation prevents cells from functioning optimally and leads to phenotypic signs of aging like gray hair, diminished organ function, and disease. He introduces the controversial but pivotal hypothesis that cells retain an underlying backup or observer mechanism storing youthful, healthy epigenetic information. By harnessing this backup, cells can be induced to reread their original correct programming, thereby reversing aging effects without erasing cell identity. Sinclair's lab has experimentally demonstrated reversible aging by manipulating key genes involved in embryonic development, notably a trio called OSK, OCT4, SOX2, KLF4, which can reset epigenetic marks to a youthful state without returning cells to a pluripotent, undifferentiated state that risks cancer. Sinclair explains the importance of DNA methylation, the addition of methyl chemical groups to DNA and histone proteins that regulate gene expression. With age, methylation patterns become disordered, causing cells to misread their genomes, turning on inappropriate genes and silencing necessary ones. This epigenetic drift compromises cellular function and drives aging phenotypes. Sirtuins, proteins discovered through Sinclair's yeast aging research, play a dual role in gene regulation and DNA repair. They maintain methylation patterns, but become distracted repairing DNA breaks, damage that increases with age, leading to less effective control over gene expression. Experimentally inducing targeted DNA breaks in young mice caused accelerated aging and methylation changes mimicking natural aging, providing strong evidence that DNA damage and resultant sirtuin diversion contribute to the aging process. A remarkable aspect of Sinclair's work is the cultivation of miniature human brain organoids, mini brains, from stem cells in the lab. These brain-like structures mimic key features of human brain tissue and exhibit aging characteristics, including reduced neuronal activity. Using this model, Sinclair's team induces aging and neurodegeneration, then tests their age reversal approaches. While these mini-brains do not yet produce Alzheimer's hallmark amyloid plaques, they display dysfunction consistent with aspects of the disease, and treatments restore neuronal firing and youthful function. The ability to study human brain aging and Alzheimer's pathology in vitro at this scale is unprecedented. Ethical questions arise regarding consciousness or sentience in these organoids, but they offer a powerful platform for therapeutic discovery that bypasses the limitations of animal models, which often fail to replicate human neurodegenerative disease. Sinclair reports dramatic successes reversing age and regenerating function in mouse and primate models. His team has regrown crushed optic nerves in mice and monkeys, restoring vision loss to nerve damage, a feat previously thought impossible given the limited regenerative capacity of adult human nerves. This approach holds promise for treating blindness, spinal cord injuries, and neurodegenerative conditions like ALS and multiple sclerosis. The treatments also reverse aging-related decline in other tissues, such as skin, liver, kidney, and muscles, by restoring youthful gene expression patterns. Studies show that de-aging cancer cells causes them to slow or die rather than promoting malignancy, alleviating some fears that rejuvenation therapies might increase cancer risk. Current experimental therapies involve introducing genes like OSK or administering cocktails of chemicals that mimic their effects. These have demonstrated robust age reversal in animals, but remain costly and complex. AI-driven drug discovery aims to simplify and democratize treatments by identifying natural or synthetic small molecules that can safely and effectively reset cellular age. Sinclair envisions future interventions as simple pills, topical creams, or sprays that engage the same pathways, enabling widespread use. Commercial and FDA-approved pathways exist in parallel. The rigorous regulatory route for novel therapies takes years to advance, while consumer products derived from natural compounds may reach the public sooner. Sinclair's lab and affiliated companies are actively developing both arms, striving for accessible, safe, and effective longevity products. Growing human tissues such as brains and uteri in vitro opens new ethical frontiers. Questions about the consciousness of brain organoids or the prospects of creating functional human reproductive organs raise societal and regulatory issues. Furthermore, translating powerful regenerative therapies into human treatments requires careful safety testing to avoid adverse outcomes like cancer or unintended tissue growth. Regulatory bodies currently mandate stringent animal and human testing protocols, exemplified by Sinclair's required experiments that blinded and then restored vision in monkeys. While these processes slow innovation, they ensure patient safety. Nonetheless, some private ventures challenge or circumvent these rules, creating tension between rapid access and responsible science. Dr. Sinclair outlines a pragmatic personal regimen supporting healthy aging, emphasizing supplements like NMN and resveratrol, both known to support metabolic and epigenetic health. Blood sugar management through diet, intermittent fasting, and glucose-lowering compounds such as metformin or berberine are key elements, as are cardiovascular supports, including nattokinase and vitamin B3, niacin, to combat inherited risks. Beyond supplements, lifestyle factors are critical. Avoiding smoking and excessive alcohol preserves brain volume and reduces disease risk. Regular physical activity, even brief high-intensity efforts, mitigates aging-related decline, while good sleep is essential for clearing misfolded proteins and maintaining neurological health. Stress reduction through mindfulness and controlled breathing further protects against accelerated aging. Sinclair's team is pioneering regenerative approaches to female fertility, including growing uterine tissue in the lab and reversing ovarian aging. Experimental evidence shows that boosting NAD+ levels can restore egg production and embryo quality even in older females, with human trials underway. The goal is to offer women the ability to conceive naturally at advanced ages or improve outcomes using rejuvenated tissues. Research in organoid models also extends to other tissues like skin and the placenta, creating comprehensive platforms for aging and fertility studies. These developments hint at a future where age-related infertility can be treated through molecular and cellular reprogramming. Looking ahead, Sinclair projects a near-term revolution pending successful human trials translating age-reversal therapies from monkeys and mice to people. If this milestone is reached, a gold rush in biotech could rapidly accelerate development across multiple organs and diseases. He envisions future treatments enabling people to maintain a biological age closer to 20 or 30 for extended periods, improving physical and cognitive function substantially. While immortality remains speculative, slowing or partially reversing aging promises significant extensions of healthspan and lifespan. Beyond pattern recognition, Sinclair describes AI systems achieving genuine creativity by proposing novel hypotheses and generating new biological models unseen in existing literature. For example, AI collaborations produced fresh predictive frameworks for biological age and detailed experimental designs, significantly enhancing scientific productivity. This evolving capacity for invention offers hope for resolving current biological mysteries, including the elusive mechanisms of cellular age resetting. Despite great optimism, Sinclair acknowledges unresolved challenges. Complete reversal of genetic mutations or large-scale DNA damage remains beyond current capabilities. Stem cell therapies face barriers to targeted cell replacement due to difficulties in cell engraftment. The complexity of human biology means full-bodied simulations at molecular resolution remain decades away. Safety concerns such as cancer risk, overactivation of pluripotency pathways, and immune responses must be addressed before therapies become broadly available. Funding and regulatory hurdles also slow progress. Nevertheless, consistent experimental successes provide a strong foundation for future breakthroughs. Multiple age-associated diseases have been attenuated in animal models. Glaucoma-related blindness has been reversed by nerve regeneration. Neurodegenerative disorders like ALS, Alzheimer's, and multiple sclerosis show signs of improvement. Kidney, liver, and skin aging have been reversed, and fertility issues are being addressed through rejuvenation of eggs and uterine tissues. Early human clinical trials focusing on eye diseases are imminent, serving as a gateway for broader applications. A key insight is that aging is not simply degradation of material components, but a loss of informational fidelity in gene regulation and cellular identity. Restoring this fidelity offers a unifying explanation for age-related decline and a blueprint for intervention. As further research unravels these mechanisms, combined with AI-driven discovery, the prospect of controlled, repeatable age reversal becomes increasingly tangible.